Well, it's my great pleasure to be here today, but unfortunately I actually wasn't invited personally, and my magnet was, so I'm not taking that too personally, and seeing as it can't talk, well not verbally, I'm going to demonstrate to you how it works, and so I need my beautiful volunteer Robina, and we've done some questions and we know that it's safe to do this on Robina. I wouldn't just do it on any of you, just like that. And we're going to talk about magnetic stimulation and can it be used to treat the brain. So this device was invented about 20 or so years ago, and it was a huge advance because prior to that, if they wanted to know how the nerves controlled movement, they used to do that with electricity, and that was pretty painful. So this magnetic field passes painlessly through the scalp. I promise you it's painless. And it's not painful anyway, and that's a huge advance on what it was like before. So it's been used in a whole number of different conditions to assess how the brain controls movement, and of course there's always that goal, can we use it to treat people that have got disorders of the nervous system? So we're going to talk a little bit about that today. So I'm going to demonstrate on Robina while we're talking here about what we do. So we've got this coil which is a tightly wound copper wire, and then we pass a large electric current through it which sets up a magnetic field which is pretty focal to just under here. So if I can find the right spot on your brain where we were before, and if I can discharge the magnet, what we might see is, that was a beautiful one, what we might see is that the magnetic field sets up a current which then passes through the scalp, sets up an electric current inside the motor part of the brain. Those nerve cells are really excitable, they're just dying to fire, and we actually stop them from firing most of the time. But when this current passes through it, we see a twitch. Now, if I had my fancy computer and my amplifiers and filters and all this sort of stuff that I normally have here, what I could show you is this is what it would look like. So we'd fire off the magnet. That first little blip that you can see just there, the first little spike is when the magnet fires, it gets picked up. We put little sticky electrodes on the muscles that we want to target, so in the hand muscles, for example, and then when we fire the magnet, 20 milliseconds or so later, you see that twitch, which we then, that's that little blip that you can see there on the screen. Thank you for being a fabulous participant for me. So that's what happens if we just fire the magnet off once. But if we actually fire the magnet off repeatedly in particular, very, very specific patterns, we can have lasting effects on the brain that outlast the stimulation. So for example, if I was to apply this pattern of stimulation here, where we have rapid bursts of stimulation, then we have little pauses. If I do this for 2 minutes or so, it can increase or ramp up the activity in the brain for a good hour or so after the stimulation. If I was to do this in a different pattern, which is more or less continuous, and for 40 seconds, that will decrease the activity in the brain for an hour or so. So because the effects outlast the stimulation, there's this hope that what if we do it repeatedly, and what dosage do we need to give to make a more lasting change in the brain that can be beneficial for some disorders? So who uses this particular technique? Well, doctors use it a lot to diagnose disorders in the pathway, say, between the brain and the hand. Psychiatrists use it for depression, which we're going to talk about a little bit later, and neuroscientists are very interested in assessing the brain and the motor system in particular, but also other parts of the brain as well, treating disorders as well, and also I use it to assess what's going on in the brain. So if we're doing particular exercises with someone, we want to know what effect that's actually having inside the brain. I'm going to talk a bit today about plasticity, and I don't mean plasticine that the kids play with, I mean the ability of our brains to change. So we used to think it was fairly fixed, that if there was a damage, you were pretty much stuck with it for the rest of your life. And although we can't necessarily grow many new brain cells, what we can do is rewire the ones that we have, allow them to make new connections within the brain. So plasticity, when I talk about it today, is really a lasting change in structure or function of the brain. And we're particularly interested in ways that we can have plasticity working for good for us, to rewire in the right way to fix damage. So one area of research that TMS has been used for in the past is to see, can it help with the brain? Can we stimulate certain parts of the brain that will help us relieve the pain that we have? And this has been done in a group of people that have got fibromyalgia, a neurological condition. They had this repetitive stimulation to ramp up the activity in the brain every weekday for 2 weeks. And what they found is, if you just have a look on the y-axis there on the left, you see pain scores. So they ask people, what's your average pain score today, ranging from 0 to 10, and obviously less pain's better. And down the bottom, we've got a whole different series of time points. So in the solid line is people that had this stimulation every day for 2 weeks to ramp up the activity in the frontal parts of their brain, compared to people that had the sham. So they sat in the same chair, they had the coil on their head, they heard a click, a very similar click, but there was actually no current passing through the coil. And they found there was a difference between those two groups of people, that the ones that had the real stimulation actually had less pain over this period. And it lasted for quite a while, up to a couple of months follow-up. So this is very new. This is only in a small number of people, but it's encouraging. You probably are thinking to yourself, well, epilepsy is a disorder where you've got unwanted excess brain activity, perhaps it can help. So I'm showing you here what happens if we record the natural brain activity. If you're just sitting there quietly with your eyes closed, then all of a sudden people with epilepsy have this activity that just goes out of control. So maybe TMS can help to reverse that hyperexcitability, and a lot of work has been done in this area. But I have to say, we're not there yet. We can't say for most people with epilepsy that we can help with this condition, because people are very tricky and they respond differently to different things for lots of different reasons. So this is an area where hopefully we will get there to work out which people can be helped. And it looks like it's perhaps the people that don't respond to medication very well that might respond to this type of technique. So perhaps we'll get there. One area that we know that the brain stimulation can help with, and that's depression. So particularly with people that have got depression that has not been treated well or hasn't been managed by medication, and they have major depression daily. Once again, they go into the doctor's office Monday to Friday for 6 weeks, and it can help to improve their depressive symptoms. So this led to TMS being used for treatment of depression in the United States. So these doctors have got these boxes in their offices and they do this treatment to people, and it does help. Now, I'm interested in people that have had a stroke. So that's an interruption to the blood supply in the brain, and some of the nerve cells die that control our movements, control our thinking and memory skills, and our speech and other areas as well. And the interesting thing about stroke is that you have this damage to one side of the brain, but it actually affects the other side of the brain as well, because normally the two hemispheres of our brain talk to each other quite a lot. And when one side's gone really quiet, the other side gets really noisy, and that can interfere with the way that we move. And it actually interferes in a lot of people in the way that they the way that they speak after they've had a stroke. So what researchers have done is they've used this technique to dampen down the activity on the so-called good side of the brain to see if we can reset the equilibrium and get a balance between the two hemispheres. And this has helped in people that have had a stroke. So aphasia is the inability to say words. You might know what you want to say, but you can't get the words out. And daily treatment with TMS has helped to balance the activity between the brains, and people could then say words that they couldn't get out before. So this is just recent studies, and this is again emerging, but it's exciting. Now, I'm very interested in people that have had a stroke, and we wonder the same thing. Well, if the orangey red area, if that's the brain damage, can we maybe the cells around that can we ramp up their activity so they can make the new connections to make up for the ones that were lost? Or, like the speech thing, should we try and dampen down the activity on the other side of the brain? And it turns out that it actually doesn't matter which one you do. Either ramping up the affected side or ramping down the unaffected side, both is significantly better than doing the sham in this group of people that had had a stroke. So they had this treatment done every day for 2 days while they were in hospital, soon after their stroke. And we've shown you here activity index scores, so basically how well you can move the affected arm and leg. And they improved in the people that had this type of stimulation. We also are interested in this ability to demonstrate plasticity. So if we just go back, this slide is taken from a study where a lot of people that had had a stroke and had weakness of their arm and they weren't using their arm, they were either given the control intervention, which was just do nothing for a year, or they were given a really, really intensive 6 hours a day of 2 weeks of intervention to improve how they could use their hand. Now, when I did this on Robina before with the coil, I held it in the one spot and we could see the response. Now, if I move the coil in a set number of positions, I can map the representation of a particular muscle in the brain, if you know what I mean. So if I move it a bit forwards, I'll get a small response and I get a larger response. And if I document all of those, the size of all those responses, I can make a map, which is what I've shown you here. So this is all the sites in the brain that will make the thumb twitch before the intervention. After they go through this intervention for 2 weeks, this intensive training, what we see up the top there is that the size of that map gets much bigger. There are much more nerve cells in the brain that can now control the thumb muscle. And that stays big 4 months later. So only 2 weeks of treatment, and then 4 months later you still see this big difference in the brain. And we don't see that in the control group. If anything, their map sizes got smaller over that period of time because they weren't using their arm. So it's very use dependent, and this is why it's really interesting that we have this technique. We can see that these people can move their hands better, but we actually know what's going on inside the brain when we do this type of thing. Now, we've done a similar study. We're interested in how sensation can help to reorganise the brain, and sensation helps us to move better. So we stimulated people's fingers and the thumb muscles and the skin and everything, send messages up to the brain to see if that would help them to move better after they'd had a stroke. Now, what I'm showing you here, same thing with the coil, but instead of moving it around, I just turn the dial and I make the magnet response a little bit stronger. And what we'd expect is, if you look at that black line, the responses should get bigger as we turn up the strength of the magnet. And that did happen in this individual. Then they went through 3 weeks of this sensory stimulation as well as physiotherapy exercises, and we looked at what happened in the brain after that, and we see a dramatic increase. The responses were 4 times larger than before this 3-week intervention. So that's really exciting, and this person could use their hand much better to do things. But I have to confess that that was on one person, and you can't make these sorts of decisions for a large number of people following stroke just on how one person responded. And when we did a trial with 10 people getting the stimulation and 10 people not getting it, there wasn't really a difference between the groups because everyone behaves differently. So we always have to keep in mind, with all this kind of experimental research, the problem is N, the number of people in the study. It tells us a little bit about how believable the results are. So the fibromyalgia study I showed you first had 10 people in each group. So it's exciting, it's encouraging, but we can't say everyone with fibromyalgia is going to respond like these particular 10 people. Whereas in the depression studies, there were over 300 people, and half of them had the treatment and half didn't, and there was a difference between the 2 groups. So we always have to bear that in mind, and that's why when people are interested in whether, can this help my stroke, so we can't really say that yet for sure because we haven't tested on enough people to know that most people will respond well to it. A large area of research is being done about whether this type of brain stimulation can help you learn. So trying to work out the mechanisms that are involved in us learning new skills and forming them into real memories inside our brain. And it turns out that our brains can't be easily tricked by this type of stimulation. And simple things really don't seem to make much of a difference. But maybe on more complex tasks, it can be useful. Now, this is a really interesting study. And, I said before that I wasn't invited, the magnet was. And then they put me on the very first talk of the day. And my colleagues at Adelaide Uni have shown that we don't really learn as well in the mornings as we do in the afternoon. So I lucked out both times there. When we do these patterns of stimulation, everyone responds differently. Some people will respond dramatically and others don't show much of a change at all. And we wanted to know what was it that made it so variable. And it turns out that it matters at what time of day you do it to people. So my colleagues, they looked at people that they did a PAS stimulation, so once again just another pattern of stimulation. They did it at 8 o'clock in the morning and then 8 o'clock at night, and they saw was there any difference between, in the same people, their responses. And they saw a massive increase in the evening compared to in the morning in the same individuals, and they wondered what that could be. And it turns out it's due to cortisol levels. So when they gave people cortisol, they didn't show the same plasticity or the same potential for rewiring inside their brains. So I have an awful lot of cortisol going around at the moment, so I'm probably not going to learn anything either. But we do all our experiments in the afternoon now as well, just so we can get a stable kind of baseline about what's going on in our brains, because our brains, of course, are influenced by the rest of our system. Now, I've talked to you now about research, and I've given you scientific references. It's all been peer-reviewed and it's all believable and all that. But now I'm going to tell you about some experimental work that I'm doing that I haven't published yet. It's not finished, but there are some ideas that we have. Now, whenever we have ideas in science, we go back and see what can we base it on. Are we making something up completely, or is there a basis behind what we do? And there is a bit of a basis behind the role that exercise can have to improve your brain. So specific hand exercises can change the brain. Like I showed you in those people with stroke that did a lot of exercises that changed their brain. Well, this study looked at what happened if we had people like we had in the chair before, and we stimulated Robina's hand and we saw it moved in roughly the same direction each time. Well, they isolated it to just the thumb movement, and they stimulated people's brains and their thumb moved generally in the same direction each time, which is what you can see in those pre-training pictures there. So they recorded the direction that they moved, that their thumb moved when they stimulated the brain before the experiment, and then they got them to move in the exact opposite direction for half an hour. These poor volunteers, I hope they got paid, because every single second for 30 minutes they had to quickly move their thumb in the opposite direction. And when they stimulated their brains again, what they found is their brain kind of remembered that. It had reorganised. They put the coil in the exact same position, and all the movements were going in the way that they had just been trained, because our brain had kind of learned that, and we'd had this short-term reorganisation. So exercise can change the brain in the short term. You can probably see there that after about 20 minutes or so, it went back to the way that the brain liked it before. My colleagues have also looked at whether regular exercise changes the brain. So they got a group of quite crazy individuals that did sort of 3 or 4 hours of really intensive exercise a day, training for an Ironman or something or other. And they compared these very, very active people who had been very active for many, many years to sedentary young university students that probably sat in a chair for 12 hours a day. And they looked at one of these plasticity kind of stimulation things and see whether there's any difference between their brains. And they were particularly interested in the motor parts of the brain. And they found that, yes, there was a difference, that the people that were very active had this greater potential for plasticity in the brain, in this short-term rewiring kind of paradigm. So this got us thinking, so these are people that exercise a lot all the time, but maybe exercise on its own, just like the specific thumb movements, maybe aerobic exercise is good for our brain. It gets various factors growing which are good for the health of our nerves and which can help our nerves to form new memories. Maybe exercise can help the brain in the short term. So we're looking at a study where we get people coming in, they either sit in the chair for half an hour, they cycle on a bike quite gently for half an hour, or they cycle a little bit harder for 15 minutes and see, does that little burst of exercise, does that change the brain? And then after that, we're doing one of these stimulation paradigms to change the excitability of the brain, and we're ramping it down to see if that has an effect. And I can show you my preliminary results so far. The exercise itself doesn't seem to change an awful lot. So the line in red is our hard exercise or the higher intensity exercise. It goes up a bit, but nothing dramatic at this stage. But when we look at what happens after we stimulate the brain, the red line shows a dramatic decrease, which is in the direction that we'd expect when we dampen down the activity in the brain, much more so than the low intensity group for sure. So the reason I get really excited about this is because if I'm doing rehabilitation with someone that's had a stroke, I want to make sure that not only do I get them to get their hands a little bit stronger or move a little bit better, but I want to change their brain. I want this to be a lasting improvement. So maybe if I get them to cycle on a bike for 15 minutes before they do their rehabilitation, we're actually putting their brain in the right state to learn and to make the right connections to make it a permanent change. So I'll keep you posted. So I think my time's just about up. So I hope that what you take away from today is that some scientists are doing some interesting work with this kind of technique to see whether it can help us to learn. It can maybe treat some disorders like epilepsy, can certainly help with depression, but I'm interested in whether we can rewire the brain following injury. We may have treatments in the future, but there's also a large amount of really interesting work being done in kids that are born prematurely and what happens to their motor system, and this can help us understand a little bit more about that. And people that have motor problems after substance abuse. So there's a whole wide range of research. Now you've seen it, you know what it's all about. Thank you.